Chapter 12, Deflection of Beams and Shafts. In this example, we want to calculate a delta at deflection of configuration at the center C. If the information provided is distributed load of 5 kilonewton all over the span of the top beam, length of AB is 2.4 meters, length of DE is 1.5 meter, modulus of elasticity is 200 gigapascal, I, moment of inertia, second moment of area or moment of inertia is 5.12 times 10 to negative 6 meter to the force. So if don't have any beam in the down section, so the maximum deflection of two simply supported beam handling a uniformly distributed load of W at its center C is delta max of 5WL4 over 384 EI. But we have extra term here, so beam D below prevents the top beam to all the way down by this amount. So it's just applying a force of, let's say, Fs to the top section, and then we can simulate the effect of below beam like a spring, which is holding the top beam to all the way goes down. So in that scenario, we can just simulate the whole configuration, a combination of a simply support beam handling a uniformly distributed W plus a spring with the stiffness of, let's say, Ks, which is the stiffness for a spring. And that's equal to, when we don't have any spring, that's all the way goes all the way down by the amount of delta maximum for this scenario plus a condition which the spring applies an upward force to the system by the effect of PL cubed over 48 EI, which is the effect of a simply supported beam with the effect of just a concentrated load either upward or downward. That's PL cubed, just replace P with force of a spring. And the same amount of F of spring applies to below beam, because that's the only effect of only force applied to the below section. And in that case, delta maximum for the down below beam DE is PL cubed Fs L cubed over 48 EI. So let's have a closer look to the problem. The stiffness of a spring is exactly the stiffness of beam DE, because we just simulate beam DE with an effect of a spring. So if delta maximum for beam DE is PL cubed over 48 EI, so one can easily say a delta K stiffness for beam DE is just a 48 EI over LDE cubed. And if you calculate that based off the problem statement, which is length of DE is 1.5 meter, E is 200 gigapascal, and I, moment of inertia, is 5.12, etc. If you replace that in the equation, it just gives you the stiffness of beam DE, which is equal to 14.5635 to 10 power of 6. Let's back to top section. So if for the top section we have a 5WL4 of 384 EI plus the effect of the upward effect of beam D, which is plus delta C2, which is FL cubed or 48 EI, and let's say for in terms of consistency of the formation, delta C in each section should be consistent to each other, should be equal to each other. It doesn't matter if it's top section or down section. Delta C has no way to move at the same amount of vertical distance. So in the part top section, we do have a this configuration of force, and in bottom section we do have a just Fs applied to the below section. So it says the effect of a W 5WL4 over 384 EI plus a upward is equal to Fs, which is here, Fs over KD, which we just calculate D to be 48 over LD cubed. So it just says if you replace the numeric value for the top section is equal to the exact displacement, so that's delta C for first section is exactly delta C in second section, and that's 5. W is 25 kilonewton times length of D, which is 2.4 meters to the power of to the force over 384 times E times I minus this time, because this displacement is downward and the other is upward, so minus this time Fs applies, so that's Fs times the same length for top section, and that's equal to Fs over Kd. If you replace the numeric value and solve the equation based off Fs, it just gives you a equation which just gives you the amount of Fs. If you do the math, it just gives you Fs equal to a 30 kilonewton, and due to symmetry, if Fs for Fs spring applies to below section, so that says Rd is equal to Re, and each of them is 15 kilonewton. And because the top section is 2.4 meters and W is 25 kilonewton, that's 20, that's not kilonewton, it's kilonewton over meter. When 2.4 times 225, 60 kilonewtons. So if the total load is 60, Ra and Rb are the remaining force, half of remaining force. That's a half of a 60, which is the total force, minus Fs, which is 30. So it just gives us all the reactions are equal to each other for this case, and they are 50 kilonewtons. And finally, delta at center is Fs over Kd based off bottom or below section, and that's Fs, which this is Fs over Kd. And if you replace that with the numeric value for Fs, which we just calculated, over Kd, which we already calculated to be 45 something, that gives us a delta C is equal to 0.6 millimeters, almost 2 millimeters vertical displacement for this category. Thank you.